At the end of the last part, I showed you that the greatest common factor of these two terms was this factor, x plus 1, and that therefore we could write this expression with the greatest common factor factored out. And what we need to multiply by this factor to get this term is 2x, and what we need to multiply this common factor by to get this term is 3. This is another way to write this expression. Notice that if I distribute this, x times 2x, I get 2x squared. X times 3 gives me 3x. 1 times 2x gives me 2x. And 1 times 3 gives me 3. I can think of this as the greatest common factor of these two terms is x. There's an x in here, and there's an x in here, but they don't have anything else in common. If I take that copy of x out, I'm left with a 2 and 1 copy of x, and in the other term I'm left with just the 3. I've taken this x out and put it here, and I'm undistributing that now, so x times what gives me 3x? That would be 3. I've written an equals here when I meant to write a plus. For these two terms, there is no greatest common factor, except for 1. Remember, 1 is a factor of everything. If I undistribute 1 from these last two terms, I get 1 times 2x is 2x, and 1 times 3 is 3. This plus sign here can be dropped down, and now I have another way to write this expression. What's the greatest common factor now? 2x plus 3. 2x plus 3 is common to both of these terms. And what's left over, what did I have to multiply that by to get this term? I had to multiply it by x. And to get this term, I had to multiply it by 1. This is actually the same thing as I had here. But the factors are in a different order. That's okay because a times b is equal to b times a. Remember, that's the commutative property of multiplication. It's just that my a and my b are much bigger pieces. But in both cases, I have x plus 1 times 2x plus 3. So these are equivalent. This is what I started with, and this was my goal. Find the greatest common factor and rewrite this expression with the greatest common factor factored out. And that's what I've done. Let's take a look at another one. In this problem, the greatest common factor to both of these two terms is y plus 5. Y plus 5 is multiplied by x in this term, and y plus 5 is multiplied by 3 in the other term. So y plus 5 is the piece, the factor, that's common to both of these terms. What did I have to multiply y plus 5 by to get this first term? X. And what did I have to multiply y plus 5 by to get the second term? 3. This is actually question number 37 in your textbook, but it doesn't start out looking this way. If I go back a step and rewrite the question as it first appears in your text, then I can show you how to get from here to here so that you can do this next step. It's not hard. We just need to build on one more thing. To factor by grouping, I'm going to start with an expression that looks like this. I'm going to break it in half. I'm going to look at these two terms and these two terms separately. What's the greatest common factor to these two terms? It's x. X is the thing multiplied by something different. X is the common factor, but just in these two terms. If I undistribute the x, then what did I have to multiply it by to get this term? And what did I have to multiply it by to get this term? I factored out the GCF of the first two terms. Now I'm going to do the same for the back two terms. What do these two terms have in common? It's maybe not quite as clear because this isn't written as 3 times 5. But if you think of it as 3 times 5, then you can see that 3 is clearly what those two terms have in common. In other words, I can divide out 3. If I divide out 3, what I'm really doing is undistributing. 3 times what? 3 times y. 3 times what to get 15? 3 times 5. There was a plus here, so there's still really a plus in this version of this expression. But look, now it actually looks like the problem I did a few minutes ago. And we already know how to do this step. This is the common factor. So factoring by grouping is a two-step process. Let's do one where we start right from this step here. This is question number 42 in your textbook. So as you're doing homework problems, this is very much like problem number 41. Not quite, but pretty close. To factor by grouping, we need to look at these two terms separately from these two terms. What do these two terms have in common? B. B times something gives me AB plus 3B. I'm undistributing. B times what gives me AB? B times A. And B times what gives me 3B? B times 3. Now let's go look at these two terms here. What do they have in common? We need to be careful here. There are two places where it's really easy to make a mistake. The first one is recognizing that the thing that they both have in common is not just the 7, but -7. They're both negative. So negative is common to both of these terms. So is 7, because this is 7 times A, and this is 7 times 3. Now that I've determined what's common to both terms, let me undistribute it. -7 times what is -7A? A. Now here's the other place where we have to be careful. -7 times what gives me -21, and that's positive 3. So notice that in this step, if you factor out a negative, it has the effect of changing the sign. But that's because distribution of a negative times a positive would have given me a negative. Now I can look at these two big terms and see what they have in common. There's a group of terms in parentheses common to both of these two big terms, and that's A plus 3. What do I have to multiply A plus 3 by to get this term? I have to multiply it by B. And what do I have to multiply A plus 3 by to get this term? I have to multiply it by -7. This is my answer. This expression has been factored by using grouping. I can check my answer by redistributing. A times B is AB. A times -7 is -7A. 3 times B is 3B. And 3 times -7 is -21. Using the commutative property of addition this time, I could rewrite this as AB plus 3B minus 7A minus 21. And that's what I started with. You don't need to do that step if you can see that this really is the same as your original expression. Okay, here's another one. We're going to factor this expression, and we're going to do it by grouping. Now, at first glance, it might seem silly to have rewritten the middle two terms as two terms. We could just combine like terms here. This would give me this expression, and they're equivalent. So sure, I could do that. But at the moment, I don't have the tools to factor this in this form, whereas I can factor it if it's in this form. So I'm going to give it to you in this form, and in a later section, I'll show you how to get it from here to here so that you can factor it by grouping. So for now, we're going to look at the first two terms and then the second two terms separately. What's the greatest common factor of these two terms here? Well, I can see that 2 goes into both of them, and there is at least one copy of x in each term. Undistributing, 2 times what gives me 20x squared? 2 times 10x. If I were distributing, I would be multiplying this, and that would give me 20x squared. Then 2x times what gives me negative 2x? Negative 1. 2x times negative 1 is negative 2x. At this point, it's worth taking a quick look at what you have left over here to see if there's anything common to these two terms. If there is, you may have got a common factor here, but you didn't quite get the greatest common factor. 10x and negative 1 have nothing in common, no common factors. So I know that 2x is the greatest common factor of these two terms. Now, for these two terms, I can see that 5 goes into both 50 and 5. So 5 is the number part of my greatest common factor. What about the variables? Well, there's an x here, but there's no x here. So there's no shared factor of x. I can't undistribute an x because there's no x here. Distributing 5 to what gives me 50x. 5 times what is 50x? That would be 10x. And 5 times what is negative 5? That would be negative 1. When you're factoring by grouping, at this point, you should be able to see, as you're building this one, that you want it to look just like this one, because the next step is going to be to write the greatest common factor of these two terms. And in this case, that's 10x minus 1. That's what these two terms have in common. What do we have to distribute 10x minus 1 by to get this term? 2x. Another way to think of this is what's left over when I undistribute 10x minus 1. What's left over is 2x. When I undistribute 10x minus 1, what's left over here? It's 5. It's the thing I had to multiply by 10x minus 1 to get this term. This is 20x squared minus 2x plus 50x minus 5 in its factored form. Remember, factors are just the things that you multiply by each other to get a product. This is my product. These are the two things that I had to multiply to get that product. So these two things are factors. So this is the factored form of the original expression. I don't care for many of the examples in this section of the textbook, so I'm mostly doing problems from the exercises. This is question number 66. It looks a little different. I have an x cubed term, an x squared term, an x only term, and a no x term, a constant. We haven't done one like this before, but the process is the same. There are 4 terms, so I'm going to look at the first 2 terms and then the back 2 terms. What do the first 2 terms have in common? Well, 3 and 4 don't have anything in common. But x cubed and x squared have 2 copies of x. In other words, there are 3 copies of x here, but there are only 2 here. I cannot undistribute all 3 copies. I can only undistribute these 2 here. When I undistribute x squared from this term, in other words, ask myself what I need to multiply by x squared to get this, I get 4x, because x squared times 4x is 4x cubed. What do I need to multiply by x squared to get negative 3x squared? Negative 3. X squared times negative 3 is negative 3x squared. So the greatest common factor of the first two terms is x squared, and what's left over is 4x minus 3. In the back two terms, the greatest common factor can only be a number, because this term does not have any x's in it. So there are no x's to undistribute from these two terms. This one has an x, but this one doesn't. What do 8 and 6 have in common? 2. What's left over? What do I need to multiply by 2 to get 8x? And what do I need to multiply by 2 to get negative 6? My eye automatically goes from here, as I'm writing this, or at least as I'm finishing writing it, to here to make sure they're the same when I'm factoring by grouping. They are the same, and that's good, because now I want to take these two big terms and find the greatest common factor to them, and I want that to be this factor here. If these aren't the same, I can't do the next step. Here they are the same. So I can say that what's common to these two big terms is 4x minus 3. What's left over are x squared and 2. The thing I had to multiply 4x minus 3 by to get this whole term here was x squared. The thing I needed to multiply 4x minus 3 by to get this term was 2. So x squared was left over when I factored out 4x minus 3, and 2 was left over when I factored out 4x minus 3. This is my answer. This is the factored form of this expression. Okay, here's my last one for this part, and I've chosen this for a very specific reason. Factoring this expression is going to be pretty straightforward. The problem is the signs. I'll show you what I mean as we go along. Since I'm factoring by grouping, that's actually the only way I know how to factor so far. I know that I need to take the first two terms and the second two terms. I need to factor the greatest common factor out of these two terms, and then the greatest common factor out of these two terms. What's common to both 6, x squared, and 9x? Well, what's common to both 6 and 9? That's 3. What's common to both x squared and x? One copy of x. I can only undistribute one copy of x. What's left over? 3x times 2x would give me 6x squared, and 3x times negative 3 would give me 9x. A positive times a negative is a negative. Now we need to deal with these two terms. What do 4x and 6 both have in common? 2. No x here, so I can't undistribute an x. What's left over? This is actually a bit of a problem area. What do I need to multiply by 2 to get negative 4x, negative 2x? What do I need to multiply by 2 to get 6? 3. The problem is, these are not the same. They're close. They're actually the same except for their signs. This is like saying the opposite of this, because negative 2x is the opposite of 2x and positive 3 is the opposite of negative 3. So this whole thing is the opposite of this whole thing. An easier way to deal with this is to observe that this minus between the two big groups can just be brought down and placed here as a minus. So let me change that, but that's also going to result in a change in the leftovers. Bringing this down, I'm now asking, what do I need to multiply by negative 2 to get 4x? 2x, because negative 2 times 2x is negative 4x. Here's our other problem area. This is a plus, and a lot of students will just bring a plus down here. But I'm undistributing a negative 2, so I need to ask myself, What do I need to multiply by negative 2 to get positive 6? Well, 2 times 3 will give me 6, but a negative times a negative is needed to give me this positive. If you undistribute a negative, it changes all the signs in the leftovers. But that's good. Remember, we want these two things to be the same, and now they are. What's common to both big terms? 2x minus 3. What's left over? 3x minus 2. 3x was left over when I divided out, or factored out, or undistributed 2x minus 3. And when I did that here, what was left over was minus 2, or negative 2. In the next two sections, your textbook takes a very traditional approach to teaching factoring. I'm going to take a slightly different approach. I'm going to show you how to get any factorable trinomial into a form that lets you use factoring by grouping. Once you have your expression written in this way, all you're doing is looking for a GCF here, and then again here, and you're done. It works every single time. There's a lot of trial and error in the conventional way of teaching factoring. There's no trial and error in factoring by grouping. There is one step that takes a little longer than the others, but once you've mastered that, you'll never have any trouble factoring again. Keep in mind that not every trinomial can be factored, but that's something we'll run into in the next section.